So hi, I'm Luke Barnett and I've been doing a PhD at Aberystwyth University and I've been making seaweed-based bioplastics. So we take the seaweed and we extract a compound called sodium alginate. This sodium alginate is a very current, novel compound that has been used previously in plastics, but the purpose of this PhD was to take it forwards a step and try and make many, many different types of plastic. Rather than just using the resource for one type, let's use it for many. What we did was make this sodium alginate and put it into solution, so sodium alginate and water solution, and we added in lots of natural biodegradable additives. Now what they did is make the molecule a little bit more complex, either give it some strength or some elasticity within the molecule, so when we cast and dry and evaporate off that excess water, what is left is a different type of plastic film with each additive we add. So we've got films that range from using the sugars, polyols, celluloses, starches. We've used many, many different things at many different concentrations. And what we've ended up with is around 100 different types of physically different plastic films, whether that changes in tensile strength, whether that changes the elastic properties, or whether that changes the film's transparency or its biodegradability. So then we took a step further than that and we wanted to include some antimicrobials into this compound, this film. So we incorporated initially a nice rounded seaweed-based antimicrobial named fucoidin. So we take the sodium alginate out of the seaweed as well as the fucoidin and then incorporate both of these into the film. This gave us some sort of antimicrobial properties, but not quite what we needed, and in terms of an antimicrobial, it's quite highly expensive. So we started to incorporate other natural biodegradable antimicrobials. So things like essential oils are very nice, quite potent as antimicrobials. Natural plant extracts like your aloe veras, your curcumin from turmeric, quite nice examples. So we incorporated those into the films and we found some really lovely antimicrobial properties against food pathogens in that. Then we moved on to our scaling up of these plastics and testing the degradability. So we worked on trying to get the plastics into plastic extruders, so the current infrastructure around for plastics. This wasn't quite as successful as we'd hoped because there are limitations on the thermal properties of biodegradable materials. Obviously, if you've got a degradable material, it's got to degrade at relatively lower temperatures compared with our plastics. So then we moved on to other more novel alternatives to this. So our main standout for our sodium alginate plastics was 3D printing. We incorporated a biodegradable photo initiator, always keeping that biodegradability as a key part of this project. Incorporated this photo initiator and then we cast the film and exposed it to ultraviolet light, which created the film. This also reduced the drying time needed to evaporate excess water by a really large amount. We're talking at least 50% decrease in that drying time, which is an amazing finding. So what we've ended up with is a really wide variety of plastics, some novel ways of creating them and making them up, and an antimicrobial add-on in there as well. One of our main issues with currently crude oil-based plastics is that they linger around in the environment for such a long time. We're talking somewhere between 50 and 1,000 years. Now that's all dependent on the environment that the plastic gets thrown into. If we end up in soil systems, under the ground, in landfill sites, or whether that's just floating around in the ocean. So a really real range of different lengths of time that these will be around, sort of minimum at that 50 years. Whereas what we need is some alternatives to that. So this alternative brings a faster degradability, but also has its use cases. So we use it for a very short lifespan. So we're sort of looking at that 2-week mark as our absolute maximum at the moment, with potential to go further should we need that by incorporating more additives into there. So our other issue is that crude oil is a very limited resource. So we are running out, it is finite, we won't be getting any more when it runs out. So we need to explore these other bio-based alternatives. So we have got plenty of other things alongside seaweed, like our starches, like our celluloses, many, many other things that add on to this, like our grasses and wheats and things that we can make plastics from. This isn't a one thing solves all. Seaweed is not the only answer. But by doing this foundational research and incorporating these additives in at the initial base, we can extend that across all our different other bio-based alternative resources. So we really have got this wide approach to making biodegradable bio-based plastics that can mimic crude oil plastics and potentially be used as an alternative resource. So what we're now going to do is take some time to show you how these plastics are made and how we degrade them.